This is problem 1428. It's on page 612. The velocities of two collars before impact are as shown. If after impact the velocity of collar A is observed to be 5.4 meters per second to the left, determine A, the velocity of collar B after impact, and B, the coefficient of restitution between the two collars. Let's sketch the problem. Basically, the two collars are just supported on a rod. And there's collar A, here's collar B. 3 meters per second and 5 meters per second are given as the speeds of those two collars as I've shown. Collar A has a mass of 2 kilograms, collar B has a mass of 3 kilograms. Okay, now when these two bodies impact each other, they're going to deform, right? Because if they don't deform, they're not storing any energy. Now once they've deformed, they're going to restitute, if you will. They're going to spring back out and push off of each other. Now the other piece of information we've been given in the problem statement is that after impact, collar A moves at 5.4 meters per second to the left. Now I've given you the equation, or pointed out in the book, the equation for the coefficient of restitution. So let's start using the terminology in this equation. The way to remember this is that the denominator is the relative velocity before impact, the numerator is the relative velocity after impact. So you tell me, which ones of these numbers that we've been given, these velocities, are which symbols? Obviously these are going to be A. They're going to be velocities. But which one is before and which one's after? That's before. So it's this one. Okay. So what do I need to do to this? I need to put a prime on it, because that's the velocity of A after impact. Okay? What about this? That's the velocity of B. This is collar B. Is it before or after impact?
Before.
It's before. So do I need a prime on it or not?
No.
Right. I don't need a prime on it. So the only unknown, well, there's two unknowns in this equation. There's the velocity of B after impact and the coefficient of restitution. So the coefficient of restitution equation itself usually won't solve the problem you've been given in these little textbook problems. Okay? So what else can we do? Well, we can deal with impulse momentum. Okay? Now here's what's really interesting. Let's write down the impulse momentum equation for this collision. We've got the mass of A multiplied by the velocity of A initially, plus the mass of B times the velocity of B initially. Now wait a second. What did I just do here? I've added two momentums together. These are two separate bodies that have momentum in different directions. Is that okay? It is. Let me go the other way though. We could say plus the impulse that occurs. Now this impulse would have deformation and restitution in it, right? It would be both of those periods together. So whatever that force is from, let's see, let me think of it, onto A from B over time, whatever that is going to change the momentum of A to some new amount, right? And we could also write a similar equation for B. The force from B onto A over time equals the mass of B times the velocity of B after impact. Okay. Now what do you know about the force from B onto A and the force from A onto B?
It should be equal.
They should be equal. In fact, it doesn't matter how they vary over time, they will both always be equal and opposite. Right? Remember Newton's laws? Okay. So that's the key, because now if I just add these two equations together, these two terms will cancel each other because they'll be exactly opposite from one another. And now what we can say is that the momentum of this system is conserved. There's no increase or decrease in momentum. Now, there will be a loss in energy, okay, because these two things are not perfect springs that bounce off of each other. Ideally, if they were, by the way, you'd have a coefficient of restitution of 1. Okay, but they're not. Even if we do a simple experiment, what about if we took a ping pong ball and dropped it? Drop it on the floor. Would it come back up to the height that I dropped it? No. There's going to be some loss because that ping pong ball on this floor will not act like a perfect set of springs bouncing off of each other. Okay? So anyway, let's add these two together. Let's just add the two equations. The mass of A multiplied by the initial velocity. I can't write and talk this morning. Initial velocity of A plus the mass of B times the initial velocity of B then is equal to the mass of A times the final velocity of A plus the mass of B times the final velocity of B. So all we said is that the initial momentum of the system equals the final momentum of the system. That's all this says. Now this is another equation that will help us out because look, we know all the masses, we know three of these velocities. The only velocity we don't know is this one. So now we'll be able to solve for the velocity of B after impact. What are we doing here? We're saying that momentum is conserved. That's all we're saying. There are no external forces acting on it. Now if there was friction, then would this work? No, it wouldn't work because there would be an external force on that system. Okay? What if there was friction and this rod was free to float around? Then it works because the friction is an internal force to the system. If this is a rod with two collars sliding on it out in space just going towards the moon and the collar A and B are moving toward each other, it doesn't matter if there's friction or not. The momentum of that whole system will be conserved. Anyway, so let's solve for the velocity of B after impact. Let's see, I've kind of run out of space. I didn't plan my board space very well. Okay. So I'll have to move up here. So the velocity of B after impact would be equal to the initial momentum okay, just copy down this side, less the momentum of A after impact divided by the mass of B. All right, so we've used this. So the mass of A, 2 kilograms. I'm not going to plug in units because we know we'll have all masses in kilograms, all velocities in meters per second. So it's pretty easy to see we'll get velocity in meters per second. Okay, so mass of A, 2 kilograms. Velocity of A, this is before impact, 3 meters per second, plus the mass of B of 3 kilograms. What is the velocity of B before impact?
5. Negative 5.
Is it 5?
Negative 5.
Negative 5. Why do we have to be careful? Because the momentum equation is a vector equation. You have to include direction. And by writing the velocity of A as positive, I have taken to the right to be positive. So you have to be really careful about that. I have to plug in a negative 5 meters per second for the initial velocity of B. So then minus the mass of A, which is 2 kilograms, the final velocity of A. Final velocity of A is how much?
Negative.
Negative. Isn't that already taken into account here? No. This is just because I moved momentum afterward onto the same side as momentum before. Okay. So I still have to plug in a negative 5.4 meters per second because the velocity of A is to the left after impact. The mass of B is 3 kilograms. So plug all that into your calculator, and you should come up with the final velocity of B.
0.6 meters a second.
To the right or to the left?
To the right.
How do you know it's to the right?
Because it's positive.
Because it's positive, that's right. If you could get a negative number out of this equation depending on the details of what's going on here. In fact, if B was very, very massive, it wouldn't be a surprise that B would just continue on, right? And A would sort of just bounce off. It's kind of like a bullet hitting a tank, right? The tank's going to just keep moving. So 0.6 meters per second, and that is to the right. So they do, in fact, bounce off of each other because the masses are so close to each other. Well, the initial momentums are very close to each other. Okay, so there's the velocity after impact. Now we can find the coefficient of restitution. Now, one thing I like to do, I don't care for the prime terminology, and so a lot of times what I'll do is I'll put an F after it. You don't have to. It's up to you. I like it that way. It makes more sense to me. Sometimes I'll even put an I on the initial velocity, so I don't forget which one's which, because I sometimes struggle to remember what the prime means. To me, a prime means a derivative, okay, but that's not the case in this equation. So anyway, the velocity of B final, let's see, we decided that was 0.6 meters per second. The velocity of A final is negative 5.4 meters per second. Again, you have to be really careful with your sign. This negative sign just comes from the equation where you need the difference between those two. And this negative sign comes from the fact that velocity of A final is against the positive coordinate, divided by velocity of A initial, 3 minus velocity of B initial, negative 5. Okay? So when you plug all of that into your calculator, this is 6/8, which is 75%. Okay, now, I want to extend this problem a little bit. That's an easy problem. Okay? I want to extend it just a little bit. Do you think any energy was lost in this process? Let's find out. How did we quantify energy? This is good from chapter 13. Kinetic energy, what's the equation?
1/2 velocity.
Good, 1/2 mass velocity squared. Okay, so let's figure out how much energy there was initially, okay? So initially, there was 1/2 mass A velocity of A squared plus 1/2 mass B velocity of B squared. Okay, if we pull out the half, mass of A is 2 kilograms. Okay, velocity of A is 3 meters per second, needs to be squared. Plus, remember I pulled out the half, so mass of B is 3 kilograms. And velocity of B initial is 5 meters per second squared. Now wait a second. I didn't plug in a negative sign for the velocity. Why not? Doesn't matter. You could plug it in, but the square is going to get rid of it because we're just saying how much energy the system has. Energy does not have direction, whereas momentum does. Okay? So there's the initial energy. I have not done this part, so why don't you plug these numbers into your calculator for me and let's find out how much energy there was initially in this system. I think I've got it. Is that right?
46.
Did I mess up?
5.5. 46, 45.
Okay, I messed up somehow. 46.5? I don't know how, I'll have to think later how I did that. So 46.5 kilograms meters squared per second squared. What kind of units of energy do we use in SI?
Joules.
Joules. Do you see joules in here anywhere? Not yet? How about if we take a meter and put it off to the side? Now what do you see? You see Newton meters. What is a Newton meter? It's a joule. So in fact, this comes out in joules. Okay? All right, I'm going to need the final velocity of B. I don't want to lose that, because now let's calculate the final energy. Same thing, 1/2 mass of A, let's just go ahead and separate it out, velocity of A final squared plus mass of B, velocity of B final squared. Okay, so 1/2, in fact, rather than me plugging it all in, you plug it all in. Let's see if you can get the right answer. So you're going to plug in the final velocity of A is 5.4 meters per second, final velocity of B, 0.6 meters per second. See what you get. $29.7. Anyone second that?
Yeah.
Okay. So that's how much energy we have after. If you take the difference between these two, you can find out how much energy was lost. So take the difference between them, if you would, please. I can do that. Start off with 16.5 and then add in 0.3, so 16.8 joules, isn't it? Okay. So that's how much energy was lost. This is really neat. Before, we haven't been able to quantify loss like this, right? We've had no way to do this. But if you want to know how much energy is lost when two objects impact each other, you can figure it out. Okay? because you can measure the initial and final velocities of the bodies, figure out the coefficient of restitution, and figure out how much energy was lost. Any questions, comments? Well, obviously you could do that, right? Because if you can measure the velocity before and after impact, figuring out how much energy was there initially and finally is trivial, right? That's easy. So where would this help us? Well, what if we bounced the two objects off at some other speeds? Then we could predict what would happen if we knew the coefficient of restitution, and there would be a different amount of energy loss, right? So we'd only need one experiment, and that would assume that the coefficient of restitution remains the same, regardless of how hard the objects bounce off of each other. We should do that as a lab. That would be interesting. We could do that. We'll have to figure out how. That would be neat. Any questions on this problem? All right.